Okay, so now we're going to be determining the pH of a weak acid. pH of a weak acid. Since the acid is weak, it will not ionize 100%, so we cannot automatically know the concentration of H3O plus or OH minus. Okay, so let's start right now with number 14 from your notes. It says determine the pH of a 0.10 molar solution of HC2H3O2. Remember, that's acetic acid. So we're given the initial concentration of 0.10 molar. The problem is not all of this 0.10 molar will turn into H3O plus and C2H3O2 minus. Whatever these numbers over here will be, something less than 0.1, and here again something less than 0.1. But I don't exactly know how much. So there's a couple clues in here that's going to help me out. First thing is this double arrow right here. This double arrow means that it turns into the ions H3O plus and C2H3O2 minus, but it turns back into HC2H3O2. But the double arrows also give me another clue. They also say that this reaction is at equilibrium. All right, equilibrium, which means that the forward reaction and the reverse reaction are happening at the same time and at the same rate. So, in order to find the pH of my solution, I need the H3O plus at equilibrium. And I have the H3O plus initially, so I can set up an icebox. All right, so my icebox is going to have something like this. I start with 0.10 HC2H3O2, start with 0 H3O plus and 0 C2H3O2 minus. The change part. Well, since I'm not given any other information, the change has got to be, I have no idea, but there, I can see that it's a 1 to 1 to 1 mole ratio, so whatever the change is going to be for one thing, it will be for all things. So can't I just say whatever the change will be here, will be the same there and there, x, x, and x? And the change for the reactants is always going to be negative because the reactants are being used. And the change for the products will always be positive because the products are being produced. So that at equilibrium, I end up with 0.1 minus x and x and x. Fantastic. Now all I need is an equilibrium constant expression to plug it into. So an equilibrium constant expression, that is K, is equal to products H3O plus times C2H3O2 minus over the reactants HC2H3O2. And there it is. Now, since this is an acid, then the K is not specifically called K. It's got a special Ka for acids. There will also be a Kb for bases, a Kw for water, and so on and so forth. All right, so now I have my icebox and I have my Ka expression. All I have to do is plug the numbers in and I'm good to solve. Now, one thing I want you to notice beforehand is that we're going to end up having a very weak acid, so this x here is going to be very small. It'll be small in all the places that we see it, but over on the left-hand side, on the reactant side, it's actually going to matter. So what we're going to say is that x, just to make the math a little bit simpler, it's going to be so small that it will be negligible, and so 0.1 minus x is equal to 0.1. I'll show you why that's going to be important in a minute and how you can figure it out. But for now, let's just assume 0.1 minus x, the x will be so small that the x will not matter. Okay, so let's just plug things in, see what we get. All right, so we have that expression, H3O plus is x, C2H3O2 minus is x, HC2H3O2 is 0.1. I'm going to leave off the minus x for now. But wait, I need something to plug that into. Okay, pause for a second and look on the back of your notes chart and let's see what you see. Did you see that there's a Ka chart and there's a Ka for acetic acid? It happens to be 1.8 times 10 to the negative 5. Well, once you have that, then all you have to do is solve for x. So let's plug it in. We have 1.8 times 10 to the negative 5 equals x squared over 0.1. We're going to multiply both sides by 0.1. And so then we'll end up with 1.8 times 10 to the negative 6 equals x squared. Then we'll take the square root out of both sides, and we'll get 3.4 times 10 to the negative 3 equals x. Fantastic. So now all I have to do is take this x right here and plug it in there, and here, and here. And then I just need to solve. Okay, so here I have plugged in my x 0.0034 as a negative on the reactant side and as a positive on the product side. Then I subtracted 0.1 minus 0.0034 to get 0.0966. I added it, 0.0034 and 0.0034. So the job actually says to determine the pH. And you remember that pH is equal to negative log of H3O plus. So that's just the negative log of 0.0034. Okay, so take a second, plug that into your calculator. And you should have gotten 2.87. 2.87? All right. So now, let's talk a little bit more about why we made that approximation that we made in the first place. A minute ago we said that x was too small to count or x was negligible. The reason why we got to do that was because of the 5% approximation, or the 5% rule. The 5% rule says that if x is less than 5% of the original number, it is considered to be negligible. Okay, so let's see if that is the case here. Okay, we've got, let's move this down here. We've got our original x was 0.0034, and the original initial number was 0.1. So, to figure out if x is within 5%, I want to take the percent, which is part, the 0.0034, over the whole, 0.1, times 100. Do that in your calculator, and you should get 1.3%. So, since 1.3% is less than 5%, that means our approximation was valid. And we could have assumed that this number is approximately equal to 0.1, and it is really, really close to 0.1. Another thing you can figure out with this is the percent ionization. Percent ionization ends up being the exact same formula as the 5% rule. That's how much of the original ionized. So if my original was 0.1 and 0.0034 of it was ionized, I can use this exact same formula to figure out my percent ionization. All right, let's try one more example. On our next example, we're going to determine the pH and pOH of a 1.0 times 10 to the negative third molar HF solution. So the first thing you always want to start with is a balanced equation. So that is HF plus water, and since this is an acid, a double arrow because it's a weak acid, but since it's an acid, it'll make H3O plus and F minus. Okay, so the next thing, I've got the information 1 times 10 to the negative 3 molar HF. This means that this guy over here is 1 times 10 to the negative 3. That's initially, and initially you have no H3O plus, you have no F minus, so some change is going to happen. I don't know exactly what, but it's a 1-to-1-to-1 ratio, which means the change here will be x, x, and x. We're going to subtract x from the reactant side, add x to the product side, so that at equilibrium we have 1 times 10 to the negative 3, and x, and x. Okay, so the next thing is write a Ka expression. K for equilibrium constant, A because it's an acid, and that is H3O plus, and F minus, and HF at the bottom. Okay, so the last time we did this, we made an approximation that 1 times 10 to the negative 3 minus x was approximately equal to 1 times 10 to the negative 3. And we said that if, as long as x ends up being 5% or less of the original number, then it will be all right. So let's try that approximation and plug it in. So take a second to look on your Ka chart on the back. You should find that Ka is 6.8 times 10 to the negative 4. And we've got x squared over 1 times 10 to the negative 3. Okay, so now we're going to cross multiply. So we're going to take this 1 times 10 to the negative 3 on the bottom and multiply it by what we have on the top. And we will get 6.8 times 10 to the negative 7 equals x squared. Let's take the square root of both sides, and we're going to finally end up with x equals 8.25 times 10 to the negative 4. Okay, so last thing I got to do is just check to make sure that 5% rule is valid, and if it is, then my final answer is x, and I'm done. Okay, so now we're going to try the 5% rule and just make sure that it all works. We had x was equal to 8.25 times 10 to the negative 4 out of the original. 8.25 times 10 to the negative 4 out of the original 0.001 times 100 in order for it to be a percent. And we end up with, take a second, calculate it, 82.5%. That is a lot more than 5%. This 82.5% is huge, which means that the approximation was not valid, which means that we are not going to be able to use this for x. Instead, we're going to have to say 0.001 minus x here, and this is not approximately equal to 0.001. It will have to be 0.001 minus x. So that means a little bit tougher to solve. Okay, so now we cannot make the approximation that x is negligible. We have to include it. So we'll have to start over again. 6.8 times 10 to the negative 4 equals x squared over 0.001 minus x. You have to include the minus x. So we'll cross multiply. 0.001 minus x times 6.8 times 10 to the negative 4 will give you 6.8 times 10 to the negative 7. Minus 6.8 times 10 to the negative 4x equals x squared. That is, I multiplied this and this. Essentially, I distributed it in. Now I'm going to put everything on the same side, so that means I'm going to add 6.8 times 10 to the negative 4x to the other side, and subtract 6.8 times 10 to the negative 7 to the other side. So I end up with x squared equals 6.8. Let me change that. That's not right. So I end up with 0 equals x squared plus 6.8 times 10 to the negative 4x minus 6.8 times 10 to the negative 7. Now all I have to do is solve for x. Alright, so now it's time to solve the quadratic equation. Do you remember the quadratic equation? X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So a is 1, b is 6.8 times 10 to the negative 4, and c is negative 6.8 times 10 to the negative 7. All I have to do is plug this in. X is equal to negative 6.8 times 10 to the negative 4 plus or minus the square root of 6.8 times 10 to the negative 4 squared minus 4 times a times c, negative 6.8 times 10 to the negative 7, all over 2a. So simplifying a little bit more, we get negative 6.8 times 10 to the negative 4 plus or minus the square root of 4.62 times 10 to the negative 7 minus negative 2.72 times 10 to the negative 6 all over 2. So x is equal to negative 6.8 times 10 to the negative 4 plus or minus the square root of 3.18 times 10 to the negative 6 over 2. So now we have x equals negative 6.8 times 10 to the negative 4 plus or minus the 1.78 times 10 to the negative 3 over 2. And so then x is equal to 5.5 times 10 to the negative 4, or negative 0.00123. So we always get two solutions in the quadratic equation. The one that's not going to work is going to give us a negative molarity. So this guy is not going to work. That means x is equal to 5.5 times 10 to the negative 4. So now we can go back and plug that into our original icebox equation. So here we have our original icebox equation. We're going to change out x and make it 5.5 times 10 to the negative 4 here, here, and there, which makes these x's 5.5 times 10 to the negative 4, 5.5 times 10 to the negative 4, and 0.001 minus 5.5 times 10 to the negative 4 is 0.001 minus 5.5 times 10 to the negative 4 is 0.00045. Okay, so let's go back to our original problem. Find the pH, and the pH is the negative log of H3O plus, and we now have H3O plus, so the pH is equal to the negative log of 5.5 times 10 to the negative 4. Let's take that number and take the log of that. We end up with 3.26. Also determine the pOH, so pOH is equal to 14 minus 3.26, and that is 10.74. Here are your final answers. All right, great job.